Hello. So moving forward, we'll be unpacking one of the most important paradigm in machine learning, that is boosting algorithm. Okay. If you're looking for a data science platform like the Kaggle or the production models running massive recommendation system at the tech companies, you'll find that ensembling methods usually dominate. But while bagging like the random forest works at building independent model in parallel to average out and reduce the variance, boosting take a fundamentally different path. Okay, so now boosting is all about sequential learning to drive down the bias. Instead of creating independent models, it trains the model one after the other in a strict chain. Each new model is specifically built to correct the exact mistake and misclassification that was made by the previous one. Think of it like a student learning a complex subject. Instead of rereading the whole textbook over and over, they focus 90% of their energy purely on the tricky practical problems that got them wrong in the last mock exam. Mathematically, the core idea that you take a collection of the weak learners model that only takes slightly better than a random coin flip, like a single split decision stump, and combine them into an incredibly strong unified model whose training error drop exponentially as you start learning more. Focusing in the same section, we'll start with AdaBoost, that is adaptive boosting. Let's kick off with the grandfather of boosting, which is AdaBoost. Imagine we have a binary classification data set where our target yi are either +1 or -1. AdaBoost navigate this data set using a clever trick, sample reweighting. Here is exactly how the algorithm works. First is the initialization. We give every single sample an equal weight of 1 by n. Everyone starts on a level playing field. Second, we train and measure the error. We train a weak learner h of t of x on the weight data. Then we calculate the weight training error e of t, which is simply the sum of the weights of all the samples that are weak learners. Third step, we calculate the learning weight alpha t. This is a critical step. We determine how much say or voting power each specific weak learner deserve in the final ensembling. The formula for alpha t is given as here. Let's unpack the intuition behind using the log odds formula. If a model get a nearly zero error, the ET goes towards zero. It's a alpha t shoots up towards infinity. That's a massive say. If its error is at random 50 ET, then the AT exactly becomes zero. It's the opinion which is completely getting ignored. Okay, and if somehow we perform worse than the random chances, the weight become negative. Means we flip its prediction. Okay, fourth one is the updating the sample weights. Now we adjust the data weight for the next tree. The formula for the given is as given here. Okay, finally moving towards the next step is the final ensembling. After t rounds, the ultimate strong classifier is a weighted majority vote of all weak learners, which formula can be seen here. Okay, now shifting more towards the gradient boosting machine, we have the GBM. AdaBoost was a breakthrough, but it was weak. It heavily rely on the reweighting of the data points, making it highly sensitive to the extreme outliners and the noisy data. So here we come with the gradient boosting machine, or the GBM. Instead of changing data weights, GBM frame boosting as an iterative optimization problem where we perform gradient descent directly in the functional state. Okay, so now we are given with this formula. Let's see how it works. If you choose a standard mean square error loss function, take the derivative of it, revealing that something is incredibly beautiful. The negative gradient specifically showcase, which is yi minus capital F t minus 1 xi, which is literally just the raw residual error. Okay, now if you switch to an absolute loss or the log loss for classification, the negative gradient automatically update to represent the directional steering force needed to minimize that specific loss. Okay, now moving forward towards once a new tree is trained on the pseudo residual, we don't need to add it to raw prediction directly to our model. That would lead to a massive overfitting. Instead, what we do, we apply a regularization called the shrinkage that scale by the learning parameter neta. For that neta, the formula is given here. The capital F of t depending upon the previous capital F of t, which is f of t t minus 1, plus the neta, which is the shrinkage parameter, into the f of t. Okay, Now moving towards the third section, we have the XGBoost. Now, while we can see that GBM is mathematically very beautiful, it can incredibly show how to train on a massive data set with the help of gradient descent. We need to faster the process. For that, we have the extreme gradient or the XGBoost. Okay, so now what happened here is XGBoost utilizes a second order Taylor expansion of the loss function which we get. So it's basically similar to the before, but to similar to the previous one, but to get a at an extreme level and at a high speed, we use this second order Taylor expansion of the loss function. This means that it calculates both the first derivative, the gradient, and the second derivative, which can be shown by HI. By setting up this second order optimization, XGBoost solve for the absolute optimized leaf weight in the clean closed form and completely eliminate the need for the linear search. Okay, WJ star can be seen here. Now, when deciding exactly where to split a node, XGBoost evaluate the structure quality of the split by calculating a precision gain matrix. So this is the formula for this. You don't need to remember this formula, but what you need to remember is that XGBoost introduced massive engineering optimization via two methods. First one is the pre-sort block structure. It stores a data in its memory block stored by feature value, unlocking and massive parallelizing across the CPU core during split evaluation. Second one is the sparsity aware splitting. It automatically learns a default direction for missing or a NAN value based on what minimizes the loss, meaning you don't need to manually input missing data. Moving towards the fourth section, we have the light GBM. It's a light gradient boosting machine. We'll take it in very raw and at a very default type because that's not so important. But what is important is we'll look into it. First of all, it's a leaf-wise tree growth. Traditional frameworks like the XGBoost grow tree level-wise, splitting every node across an horizontal level evenly. Light GBM grows tree leaf-wise. It evaluates all the available leaves across the entire tree and split only the single leaves that promises the absolute maximum drop in the loss function. Second is the gradient based one side sampling, GAUS. Light GBM realizes that the sample with the tiny gradient are already well trained, so they focuses on them is a waste of time. Okay, so GAUS keep all the samples with large gradient and random samples of a small fraction of the samples towards a small gradient. To keep the data distributedly balanced, it scaled the light gradient sample by a constant multiplier during the split evaluation. And this is how GAUS help in this process. Third one is the EFB, exclusive feature building. High dimensional data is often incredibly sparse, meaning that many features are really non-zero at the same time. Okay, so what EFB does it? EFB safely blind these exclusive feature together into a single combining dense feature, drastically cutting down the total feature count that the algorithm has to evaluate. Moving towards to the last section, that is the CAD boost, categorical boosting. Basically, CAD boost completely eliminate the problem of the target leakage. First of all, what is target leakage? If you use a standard target encoding where you replace a text category with the average target value of it rows, then you will introduce several target leakage. Okay, so to solve this, CAD boost completely eliminate this technique via using ordered target statistic. It introduces a synthetic artificial time dimension by shuffling the dataset randomly. Okay, and then we compute the target statistic for a specific row. The formula for it's look like this. Basically, it's not a formula; it's for the permutation of the weights, which we can see here. So, and one more point additionally, that CAD boost utilizes symmetric tree. Every single node at a given depth evaluate the exact same split condition across the entire layer. Okay, so this highly constrained structure act as a powerful regularization. Yep. So here we have completed with all the five important boosting techniques, that is AdaBoost, GBM, XGBoost, Light GBM, and the CAD boost. Yep. Thank you.